Infodump, the series where I do a deep but not necessarily scholarly dive into a particular topic. Now, of course, we are continuing with our first topic of physics from last week, and if you don't remember fully, last week was mostly about how the Enlightenment was this sort of realization and codification, in a way, of these scientific ideals, mostly thanks to the fact that science became part of the culture of the nobility, meaning that it not only got state funding, but was a sort of imperative for the estate and for the upper class, again ensuring funding, but also ensuring that whatever results were achieved were particularly spectacular and quote-unquote better than the results achieved by any political rivals of the sponsors. You could argue that that still happens today. I would neither agree nor disagree with that assertion. Point being that, well, the Enlightenment was sort of the birthplace, the crucible, the foundry, whatever you want to call it, of the modern, or at least early modern, idea of science as this pursuit of knowledge for knowledge's sake, and maybe also a little bit for, you know, the sake of appearing to be a well-learned and well-respectable aristocrat. Of course, as I sort of hinted at last week, that is not where the story ends. We move pretty much immediately from the Enlightenment into the Scientific Revolution and the Industrial Revolution. Now, these two really went hand in hand. You had the Industrial Revolution giving more credence to, you know, many theories and many ideas that have been floated around by showing a concrete, practical use. Additionally, the Industrial Revolution helped show the value of things like experimentation and empirical data, as opposed to just theory crafting. Now, just because the smart people decided to start making steam engines and Stirling engines and whatnot does not mean that everything all changed and we got our modern conceptions of science overnight, etc., etc. No, it was this gradual process. But another big thing that the Industrial Revolution brought for science was schools. See, with the dawn of, you know, factory manufacture, there was also the dawn of mass employment, if you will. Rather than people just being peasants, instead they were, well, laborers working to create goods in factories, for the most part. That doesn't mean that peasants completely disappeared, or it doesn't mean that manorialism and feudalism disappeared. No. Again, this is a change that took a very long time. To an extent, it was already kind of underway in some countries before the Industrial Revolution, with the growth in power of various merchant guilds and artisans guilds and what have you, driving a growth in sort of production by hand. But then that just got completely knocked out of the park by everyone's favorite, the steam engine and the Industrial Revolution. All of a sudden, you had the, not what we would now call assembly lines by any means, but the standardization of labor. Not the standardization of parts or anything like that, but the idea that one person's labor was interchangeable for another person's labor, and you want to have as many people as possible working on this given thing. That requires mass training for that sort of mass employment and mass labor. So that led to the creation of what we would now consider public schools. Now, that is not to say that public education had not existed beforehand. Far from it. However, the public school system as it exists today was actually cobbled together from a model introduced in Prussia to teach young people how to be effective military leaders, as well as various American principles and innovations made to essentially train people from an early age to basically automatically or instinctively operate in a factory-like sort of setting, with a bell signaling the start and end of shifts or classes, with a prescribed lunch break, etc., etc. Prior to this, most education was either through the church or through private tutors, if you could afford such a thing. It was very rare to have actual proper public schooling, or even mass private schooling, really. Now, as someone who has been in both the public and private, modern day, present day, whatever you want to call it, school system, I personally think that the whole thing was just a little bit too industrialist for the sake of anyone but the people at the top. So that's my stance on the matter. But whether you think it was wrong for factorialization to be brought into schools, or, you know, a worthy cost for having public education as we now know it in the first place, that's entirely up to you. I'm not necessarily here to opine on things like that. What I am here for, though, is creating a bit more of a narrative and an understanding of how things went, to help explain how things are today. So, with that, we ended up with this standardized, proper, school system, which also meant that now there was an opportunity for students to learn more than just what was, strictly speaking, needed for those factory jobs they were being trained for. This brought sort of the fusion of the college environment, as it had existed up to that point, and those public school systems, that created what we would now consider a public school system, where it is not only mass training of employees, including children, because this was well before child labor laws were passed, might I remind you. In fact, it's why child labor laws were passed in many cases. So, there was a great deal of pressure to increase the scope of these schools. And that led to the creation of what we would now consider public education properly, rather than just public job training, essentially. And even then, it wasn't really entirely public for the most part. It was employers. The Industrial Revolution was basically an anarcho-capitalist's dream to an extent, but as the government started trying to provide more services to help those corporations get a foothold, that also meant that the government now had to cede to some of the demands from, well, educators, saying, hey, if we've got all these young people in the same room and we're trying to teach them something, we might as well bring in more than just the bare necessities for life. We might as well try and increase their understanding as well. Again, that is one of the concepts that largely came out of Prussia and those military academies, where the idea was the more understanding you had of the world, the more effective you would be able to be at manipulating and controlling it in the form of a battlefield. The better you understood people, such as through literature and art, the more you would be able to lead people or understand how the other side is being led. Bismarck was an absolute mad lad. That's all I have to say on the matter. But with that dawn of public education, with this gradual increase in the availability of, students to be taught, well, that also meant that there were more people coming of age with some amount of education. Not only was science far more accessible than it had ever been, it was also more advanced than it had been up until that point. Which goes, pretty much without saying, at least in the West, for a few hundred years by that point. But what's important is that union of accessibility and advancement created the scientific revolution. That really was when things got rolling on what we now consider not just physics, but many, many branches of science. But since we're just trying to talk about physics for now, that's where we're going to focus. Many big names, even in modern physics, were significant figures from the 19th and even late 18th centuries. It's always a bit jarring to be reading textbooks and then see names with the 1800s before them, because we usually, in our modern sort of high school level conception of physics, we usually think of modern physics as having really started with Einstein. Or if we really want to stretch it, we can push it back to the first introduction of quantum theory around the time of World War I, which even that feels a bit crazy to say, thinking that this idea that still feels so new is actually over 100 years old at this point. Now, with that said, this is where physics started to fracture. This is where we started developing new disciplines within physics that eventually branched off and became their own things. For instance, chemistry started splitting off from physics, because, well, we had Mendeleev and his periodic table around this period, more broadly speaking anyway, which of course meant that chemistry was now a whole lot easier to classify, because there was this generally agreed upon and generally recognized system for classifying the elements and for their properties, and it helped show how their properties worked, at least mathematically speaking. This was, of course, before there was a solid understanding of how it worked physically speaking. But the math was there. There were repeating patterns. There were, these distinct escalating steps on the periodic table. And as more and more elements were discovered, that became clearer and clearer, and it became this very rigidly defined mathematical structure that we then later figured out the actual physical groundings for. And we're still, to an extent, figuring it out. We know that electrons behave in particular ways due to quantum interference and whatnot, but we're not entirely sure why they behave in the exact ways that they do so reliably. And of course, that's something that we won't understand for at least a little while yet. But chemistry, like I said, had started, and really, by the time the scientific revolution ended, completely split off from physics. That's also where you start seeing the development of early electrical theories about how the electrons work, and about how nuclei work and what they are. The idea that nuclei might not be a single sort of mass, but rather composed of a bunch of different parts, the same way that what appears to be a solid mass from our macroscopic perspective can actually just be a whole bunch of tiny little atoms joined together. Because you might remember, actually, on the topic of atoms, since I haven't mentioned this, I mentioned way back when that there was early atomic theory in ancient Greece. The idea that there was this infinitesimal, indivisible bit of matter that you would eventually get to if you cut something in half enough times. Eventually you run into that rounding error, right? And they were eventually proven right, even though they were laughed off both when the idea was first pitched and when it was later floated during the Enlightenment and scientific revolution. Because, well, it seems a little bit crazy when you think about it. We can't, they're so small, we can't really conceive of them very easily unless we already know for a fact that they exist. And just with 18th and 19th century technology, it was very hard to definitively prove, at least at first, that atoms existed. But eventually, they managed to pull it off. Now, the main people we have to thank for atomic theory are Democritus from ancient Greece, and then eventually John Dalton around the turn of the 19th century, who sort of resurrected Democritus's ideas. He mostly figured out from working with gases that atoms were definitively real, because he decided that if he couldn't find any better or more sensible reason for the behavior of gases than them being made up of incredibly small, tiny little bits of stuff just bouncing around, then they were probably just made up of tiny little bits of stuff bouncing around. And as he continued that research, continued all of that science, he ended up, well, creating sort of pre-modern, if you will, atomic theory. Now, this was a theory that operated under the assumption that atoms were basically just these tiny little spheres that were, as their name translated from Greek implies, indivisible. Of course, we now know it's much more complicated. You can, in fact, divide an atom. That's how chemistry works, because there's the electrons around the nucleus, and those break off or are shared or what have you. We also know from the Manhattan Project that you can divide an atom in other ways, much more destructive ways. Although if you're real clever about it, you can use those destructive powers more productively. Now, over time, experiments with things like vacuum tubes were eventually used to develop more sophisticated ideas and understandings of the atom, but those mostly came about 100 or so years after Dalton. It was really mostly his experiments with gases and his mathematical proofs that they had to behave in this particular way for them to make any sense that gave us modern, or again, really pre-modern, atomic theory. Now, atoms weren't the only concept that were advanced and developed during the scientific revolution. There was a whole lot of progress made outside of physics, but in physics as well, there was the idea of, again, these sort of splinter disciplines. But most importantly, there was a sense that as technology was progressing, so too was the ability to do science. And that was sort of a key new idea. It seems sort of brain dead to us in our modern world, where we hear about things, like CERN with the Large Hadron Collider. But back in the day, sure, you knew that you needed certain, equipment and materials in order to be able to do scientific experiments, but now we were actually seeing that these advancements in technology could be directly used to further experiments in science. And not only that, but it was possible to look at the experiments that we wanted to do to answer the questions that we had, figure out what the technology we would need would be, and then set about trying to figure out how to develop that technology. So this is when you start having a bunch of people from different disciplines of science working together to solve a single problem that might not necessarily concern all of them, but does concern all of their fields at some step of the process. Now, this is where I'm gonna fast forward a little bit, because most of the progress made in the scientific revolution really had to do with what we've already talked about in terms of physics and other disciplines. Huge leaps were made in things like biology. Germ theory came about during this period of time. Essentially, most of the scientific revolution boils down to just because we can't see it with the naked eye doesn't mean it doesn't exist. just because we can find another explanation for it that relies on some sort of ontological shenanigans or divine intervention or what have you, does not mean that the scientific explanation is invalid. Just because it contradicts doctrine does not mean the scientific explanation is invalid. Yada yada. It's just a lot of these ideas being put to the forefront and then proven right that, from our modern perspective, hopefully, we think of as, you know, big no-brainers of like, yes, of course dogma does not disprove fact. Why would you ever say that? But back then, you know, with a lot of the ideas floating around about, you know, the divine and what have you, of course there was the multiple different waves of spiritualism and religious fundamentalism that swept across most of the world. But ultimately, it did end up resolving into this sort of sense that empiricism and science were the way forward in our understanding of the world, rather than trying to continuously interpret and reinterpret things like the Bible or ancient Greek philosophy or ancient Greek science or what have you. Now, that is all well and good, but it doesn't really get us much farther in physics. So we're going to skip ahead to around the end of the scientific revolution and the beginning of the modern period. And in physics, that shift is really marked by the discovery of the electron. Or more accurately, the conclusion drawn that the electron must exist and the ensuing hunt for it. Because again, this was a bit of a new step in physics. This was saying, okay, we know that this thing exists, not because the ancients are said to have discovered it, not because it should exist because I want it to, not because the holy books say it does, but because the data requires it to make any semblance of sense. This was the point where the requirements of the data started to become the driving force in physics, where it stopped being a question of how do things work at all, and turned into, well, where's this thing that's required for everything to work? Because it's required by the data, and I can't find it. So either the data's wrong, in which case we need new experiments, yay, or it's hidden somewhere and we need to do more experiments to find it, double yay. Of course, as I said, that is a gross oversimplification, but it does really bear out, because the electron was required to exist by the data. There was this discovery about the charge differential around atoms. There was the discovery that electrical currents and the mathematics behind them made the most sense if there were discrete charged particles moving to create those electrical currents, and that led to all sorts of research being done to try and isolate the electron. Now, as we know, that's a very, very hard thing to do unless you are operating with the sort of technology we have nowadays, thanks to being able to understand what the electron is and how it works. So, of course, it was not easy back then. Lots of experiments were done. I'm not going to go too far into them for now because they are mostly on the chemistry side of things. But suffice to say, over time, the electron was sort of narrowed down and discovered. definitively. Additionally, Niels Bohr, a famous physicist, put forward what came to be known as the plum pudding model of the atom. This was by far the second most inaccurate portrayal of the atom, after Democritus and Dalton's portrayal of them as just sort of spheres. Yeah. The basic idea of the plum pudding model is that atoms are sort of positively charged sphere soup things, morasses, really, with these electrons embedded as distinct points. Again, this is the second most wrong. The only reason it is not the absolute most wrong is because rather than being completely off base, it's just backwards and a little bit wrong on top of that. And at least if you get something backwards, you have the general principle. Sure, it's in reverse, but it's the general principle. Then, of course, there came the most famous model of the electron in an atom. This is the one that we still see all the time today. If you've ever seen a depiction of an atom as anything other than a sphere, you have seen the solar system depiction. Whether it's all laid out as concentric circles or rendered in 3 dimensions with the sort of like crisscrossing circles, it is the model of the single positively charged nucleus at the center with the with the electrons on discrete orbitals outside of it, spinning around, whizzing by, etc., etc. Now, this is much more accurate than the plum pudding model. It is much more accurate than the good old-fashioned sphere model. It's also not quite accurate, but it's the most common and the most popular because much like how Newton's laws work when you simplify them down from Einsteinian relativity, well, the orbital model mostly kinda works for most sets of atoms under quote-unquote normal circumstances. Now, the reality, which was put forward and proven not too much later, but is much harder to visualize and much harder to make, classroom interactables out of, is the quantum theory of the atom. Now, as it specifically pertains to electrons, the quantum theory, which so far has been shown to be the most accurate and the most correct, is essentially that you have the central nucleus. Yep, okay, good, got it. We've established that that's correct. We know that those work. We've split them. We know they're real. But then around that, rather than these distinct rings or orbitals of electrons, you have a cloud of probability. Now, those probabilities are the highest along those specific ordered interval rings. So it's most likely that an electron will be on one of those, and it's most likely that it will be on the quote-unquote correct one based on the atom's energy and number and charge / ionization / whatever you want to call it, etc., etc. It's most likely that it will be on the correct one, quote-unquote correct. However, there is always the non-zero chance that it will be somewhere else within that cloud. And that is why people hate quantum mechanics, because everything is always, well, there's a non-zero chance. If there is one thing we have learned from quantum mechanics, well, it's that nothing is certain except uncertainty. And that right there is the uncertainty principle. Sort of. But that's something for next week. For now, I think I'll just leave you folks off, having talked about the atom and how it was reproven, how it was developed as sort of the symbol, in a sense, of physics, because it was not just the frontier at the time, it was also, well, the frontier for a great deal of the future. Even now, we're still trying to figure out how to do more stuff with atoms. And by that, I mean we've figured out how to use them for shenanigans in chemistry. We've figured out how to rip them apart. And now, we're just trying to put them together. Because we know that we can. It's just a matter of doing it without blowing up everything in an entire city. So, thank you very much for watching and or listening, and I will see you next time.